Have you ever felt that, familiar overwhelm being surrounded by information? Maybe you're prepping for a really crucial meeting or trying to rapidly grasp a whole new field. Or perhaps it's just that insatiable curiosity kicking in. The challenge is always the same. How do you quickly cut through the noise, truly understand complex topics, and, well, emerge well-informed without getting lost down some rabbit hole? Today, we're taking a deep dive into a technology that does exactly that for our digital world, often silently behind the scenes. We're talking about XML, the extensible markup language. It's far more than just a file format. It's really a foundational pillar. It underpins everything from how data is stored and exchanged to how websites communicate and even how vibrant images are rendered. For this deep dive, we're pulling insights from a really comprehensive source, beginning XML, 5th edition. And here's something interesting from the source itself. Despite that beginning title, this book dives, headfirst into real-world advanced concepts. It really reflects the true complexity and sheer ubiquity of XML in modern IT. Our mission today is simple. Give you, our listener, that shortcut to understanding XML. We'll peel back the layers on its core principles, explore the huge ecosystem of related technologies, and highlight its practical real-world applications. By the end, you'll see why a solid grasp of XML is genuinely essential for anyone dealing with digital data today. So let's set the stage a bit. What was the massive problem that XML burst onto the scene to solve? Imagine the digital world before XML, a true Wild West, really, dominated by proprietary binary file formats. Think back to those old Microsoft Word.doc files. Your valuable data was basically imprisoned inside the application that created it, turning cross-platform data exchange into, well, an absolute nightmare. Data silos everywhere.
Exactly. And what's fascinating is that XML was conceived precisely as a liberator for that data. Its dual purpose was pretty revolutionary at the time. First, make passing data between wildly different software components much, much easier, lifting that constant worry about, disparate formats. And second, and this is crucial, it was designed to be easily readable by both software and humans. Contrast this with binary files. Yes, they're concise, efficient for network transport, sure, but utterly opaque without the specific creating application. Just gibberish. Text files, on the other hand, yeah, human readable, but often lack the necessary metadata to make automated sense of the data, just raw strings.
Right, context was missing.
Precisely. Let's use a simple example from our source. Imagine a plain text list. Joe Fawcett, Danny Ayers, Catherine Middleton. You only know that's people because, well, you're human, you can infer it. Now look at the exact same data in XML application user first name, Joe last name. Fawcett user first name, Danny last name Ayers, user first name. Catherine last name Middleton, application users. Instantly, the individual pieces, first name, last name, the idea of a user are clear. Even if an application doesn't fully understand the meaning yet, the structure is there. It's self-describing.
The clarity is undeniable. You can almost instantly grasp the structure. But looking at that example with all those extra angle brackets and tags,
Yeah.
it seems a lot more verbose than the plain text.
Yeah.
A lot bigger.
You've hit on a critical design decision. The XML creators explicitly stated terseness is not an aim. This was a conscious choice that, as our source notes, many would later come to regret. A bit controversial, maybe, if you analyze that application user's example, the raw data, 43 characters. The XML markup adds 130 extra characters. That's over 300% increase. Yeah. You can almost hear the network engineers groaning back then. But the creators weighed that bite count against the power of self-describing metadata. And they chose metadata. They prioritized universal understanding over minimal file size, betting that, bandwidth and processing power would eventually catch up.
Which they largely did, I suppose.
They did. It was a long-term bet that paid off.
Okay, so that problem of proprietary formats is clearly solved. But once we have this new universal language, what are the absolute must-follow rules? The grammar, if you like.
Yeah.
What makes an XML document well-formed so any standard parser can read it?
Right. At its heart, a well-formed XML document is built from three core things: elements, attributes, and one single unique root element. Elements are defined by a start tag, like my element, content inside, and an end tag, like my element. Or they can be self-closing, like user nets. Attributes provide extra info inside the start tag, like user first name Joe. That first name is an attribute. Critically, all elements must be properly nested. No overlapping tags. Think of them like Russian dolls.
Okay, everything fits neatly inside something else.
Exactly. And there must be one and only one root element that wraps everything else in the document. Beyond that, naming rules. Element and attribute names can't have spaces. Names, starting with XML, any case, are reserved, don't touch those, and XML is case sensitive. So my element and my element are totally different. It's usually bad practice to have names that only differ by case, though. Leads to confusion.
Yeah, I can see that causing headaches.
Definitely. Finally, special characters. Things like mark have special meaning in markup. So if you want to use them as actual text content, you have to escape them using entity references. Becomes an alt and becomes an ARP and so on.
Okay, so the parser doesn't get confused.
Precisely. Now, if you have a big chunk of text with lots of these, like maybe some JavaScript code inside an XHTML page.
For just like XML-based HTML, right?
It's stricter.
Exactly. Stricter rules, proper nesting. Anyway, escaping constantly in that block of code gets tedious. So for that, you can use CData sections. It basically tells the parser, ignore markup in here, just treat it all as plain text.
Ah, like a temporary off switch for the parser rules. Kinda, yeah. For that specific block. The main takeaway here is, follow these rules, and any standard XML parser can handle your document. It avoids so much unnecessary development pain trying to fix bad input.
That structure makes sense. It brings order. But what happens when you need to combine XML from different systems? Imagine merging documents. Maybe one system uses title for a book title, another uses title for a person's job title. How does XML handle those potential naming clashes?
Ah, yes. This is where XML namespaces become absolutely essential. They are the solution for differentiating elements with the same name. They let you combine XML from different sources without conflict. Think of it like giving elements a surname to make them unique. Namespaces work using URIs, Uniform Resource Identifiers. Something like http.www.w3.org 2005 atom for atom feeds. That URI is the unique identifier. You'll often see these URIs associated with prefixes, like atom.title. But, and this is vital, the URI is the real identifier. The prefix is just a local shorthand, a convenience.
That's a crucial distinction. So the prefix is just a shortcut in that specific document.
Exactly. The parser always resolves the prefix back to the full URI to understand which family that element belongs to.
Could you, theoretically, use two different prefixes for the same URI in one document?
You could, yes. The parser would understand they refer to the same namespace. It might confuse a human reading it, though.
And the opposite, same prefix, different URIs.
Also, technically possible within the rules of prefix declaration, but extremely bad practice. It would definitely cause confusion. You stick to clear conventions. For instance, there's the MathML namespace, http.www.w3.org 1998 mathML, for describing math formulas in XML. Its URI is quite verbose compared to just writing an equation normally. But again, it's designed for unambiguous software processing.
Precisely. They prevent chaos when you integrate data, allowing for robust, extensible XML systems. Okay, so we've got well-formed XML. We can handle name clashes with namespaces. But being well-formed isn't always enough, right? How do we ensure an XML document follows a specific blueprint or vocabulary? You mentioned earlier the first mechanism was DTDs, document type definitions.
That's right. DTDs were the original way to define the allowed structure. They specified the content model for elements. Could it contain other specific elements? Text, both, or nothing, empty. They also let you define attributes using atlas declarations. You could say if an attribute was required, #required, optional, #implied, had a fixed value, #fix 1.0, or a default value.
So #fix was good for things like version numbers.
Exactly. Version C data, #fix 1.0, would ensure that attribute always had the value 1.0. DTDs could be defined inside the XML file itself, or more commonly, referenced externally using a doc type declaration near the top of the XML file. They're a big step towards ensuring consistency.
They sound useful for their time, but I gather they had limitations. What came next? What offered more power and flexibility for validation?
The big successor was XML schemas, often called XSDs. They brought several major advantages over DTDs. First, and this was huge, XML schemas are themselves written in XML.
Ah, so you could use the same tools to work with schemas as you use for your XML data.
Exactly. Unlike DTDs, which had their own unique non-XML syntax, that made tooling much easier. Second, schemas fully embraced and supported namespaces, which DTDs only handled in a very limited, somewhat bolted-on way. Third, and this is where schemas really pull ahead, rich data typing. DTDs basically only understood text. Schemas distinguish between complex types elements that can have attributes or contain other child elements and simple types elements that just hold text content.
Okay, so more precision about the content itself.
A lot more precision. Schemas come with a whole library of built-in simple types like string, decimal, integer, Boolean, various date and time types like date, time. And here's the really powerful bit. You can create your own data types derived from these by adding restrictions. These are called facets,
Facets, like what?
like setting a min length and max length for a string, or using a pattern, basically a regular expression, to enforce a specific format, say for a postal code, or min inclusive and max exclusive for numbers. You get very fine-grained control.
That sounds much more like programming types.
It is much closer.
Mm.
Schemas also allow for more sophisticated content models, supporting concepts vaguely similar to object-oriented ideas like type substitution, which DTDs couldn't dream of. And they support modularity much better. You can use include to bring in definitions from another schema in the same namespace, or import to bring in definitions from a schema in a different namespace. It promotes reuse.
Schemas sound like a massive improvement, much more expressive. But even with all that power, are there still validation rules they can't easily handle? This raises an important question. When do even DPDs and XML schemas hit their limits? Are there scenarios they just can't cover?
Absolutely, that's a great point. While DTDs and especially XML schemas are powerful for structural and data type validation, they struggle with complex business rules or constraints that span different parts of the document. For example, a rule like, if this type attribute is set to urgent, then that due date element must be present and be within 24 hours. That kind of cross-element dependency is very hard, often impossible, to express purely in XSD.
Really tricky contextual logic.
Exactly. And that's where other validation languages come in. RLAXNG is one alternative, but the one that really shines for these kinds of rules is Schematron.
Schematron, how does that work differently?
Schematron's power comes from using XPath expressions, the same language we use for navigating XML to define its validation rules.
Okay, so if you know XPath, you have a head start.
A huge head start. It allows for incredibly flexible assertions. You can easily compare values across different elements, like checking min price is less than or equal to max price. Crucially, Schematron isn't limited to just elements and attributes. It can target and evaluate rules on comments, processing instructions, things DTDs and XSDs largely ignore. It uses assert elements for rules that must be true, failure is an error, and report elements for rules that, if true, generate informational messages or warnings. It's perfect for those nuanced, context-dependent business constraints.
Very clever. Using the navigation language itself to define the validation rules.
It's a very elegant approach for those specific kinds of problems.
Okay, so we've parsed our XML, maybe validated it with a schema or even Schematron, now it's loaded. How do applications actually work with it in memory? The most common model, historically, is the Document Object Model, or DOM. It represents the entire XML document as a tree of nodes in memory. Every element, attribute, text bit is an object. It's widely supported, especially in web browsers, which is why it became so popular. But the DOM can be, well, unwieldy and difficult to use sometimes, especially for complex navigation or manipulation.
And I remember you mentioned memory issues.
Yes, it's a memory hog. Our source mentions a 1 millibit XML file can easily take up 5 millibit or more of RAM when loaded as a DOM tree. Not great for really large documents or systems with limited memory.
So what's the alternative?
A more modern and in many ways more powerful model is the XQuery and XPath data model, usually called XDM. This is the underlying data model used by the later versions of XPath 2.0 and onwards, XQuery and SSLT 2.0 onwards. It offers more sophisticated handling of data types and sequences, making it much more powerful for complex queries and transformations.
Okay, XDM sounds more advanced. So let's say we have this tree, maybe a DOM or an XDM representation. We need to find specific information. You mentioned XPath.
Yes, XPath is the key. Think of it as the GPS for your XML document. It's a language designed specifically for navigating that tree structure and selecting nodes, elements, attributes, text, etc. It uses a path-like syntax, similar to file system paths. Application user would select all the user elements directly under the application user's root element.
Simple enough for basic paths.
It gets more powerful. You have the concept of a context item, the node you're currently at. Then you use axis to navigate child, selects direct children, descendant, selects children at any level below, attribute, selects attributes, often abbreviated with at, parent, ancestor, following, sibling. Lots of ways to move around.
So you can precisely describe the relationship you want to follow.
Exactly. And then you use predicates, expressions, and square brackets to filter the results, like application user at I add Armstrong John, to find the user with that specific ID attribute.
Okay, the add for attribute, then the filter in brackets.
Right. And an interesting detail, the operator in XPath works on sequences. A is true if there's at least one item in sequence A that matches at least one item in sequence B. It's not always a simple one-to-one comparison.
Ah. That's subtle, but important for handling lists of values.
Very. XPath also has a rich library of built-in functions, things like string lengths to get the length of text, contains to check for substrings, count to count nodes, and even deep equal to compare two entire XML structures, which is super useful for testing transformations.
So XPath lets us pinpoint the data, but what if we need to fundamentally change the XML? Transform it into a different structure, or maybe into HTML for a web page?
That is precisely the job of XSLT, Extensible Style Sheet Language Transformations. Its core purpose is transforming XML documents into other XML documents, or even into text formats like HTML, CSV, you name it. It's described as a functional language, which can be a bit different if you're used to procedural programming.
Functional? How so?
Instead of writing step-by-step instructions, you define templates. Each template has a match attribute that uses an XPath pattern to specify which nodes in the source document it applies to. Inside the template, you define what the output should look like when that pattern is matched. It's more declarative. When you see this, produce that.
Okay, rule-based transformation.
Exactly. The main elements you use are xsl.stylesheet as the root container for your rules. xsl.templateMatch defines a rule. Inside a template, you might use xsl.value-of-select to pull out text content using an XPath expression. xsl.applyTemplates is key for recursive processing. It tells the processor to find the best matching template for the children of the current node. This is called push processing. Or you can use xsl.forEachSelect to iterate over a set of nodes you select explicitly. That's more like pull processing.
Push versus pull. Different ways to control the flow.
Right. XOT also has conditionals like xsl.ifTest and xlo.choose, which is like a switch statement. And you can reuse code with xsl.include and xsl.import. And XSLT 2.0 really upped the game. It added better support for XML schema data types, the ability to define your own functions, creating multiple output documents from one transformation.
Multiple documents, that's handy.
Very. And powerful string manipulation using xsl.analyzeString, which uses regular expressions. Our source even notes this feature is so powerful you can use XSLT 2.0 to parse and transform non-XML input, like flat CSV files, into XML or something else.
Wow, XLT is more versatile than I realized. Okay, so it's great for transforming, but you mentioned another language, XQuery. This raises an important question. XSLT is for transforming, but what if your main goal is really just to query? To efficiently pull specific data out of potentially huge collections of XML, maybe even stored in a database. Is XQuery better suited for that?
That's exactly the distinction, yes. XQuery is designed specifically for querying XML data, or more accurately, querying data represented in that XDM model we talked about. It's optimized for searching and extracting information, potentially across multiple documents or from native XML databases.
So less about changing the structure, more about finding and retrieving.
Generally, yes. Though it can construct new XML results, a key difference from XSLT is that XQuery itself is not written in XML syntax.
Okay. What does it look like then?
It looks more like a traditional programming or query language. It's often described as less verbose to write than XSLT. It uses braces to enclose expressions that need to be evaluated, similar perhaps to PHP or JavaScript embedding. Its core construct is the FLWAR expression, FLWOR.
FLWAR. What's that stand for?
For let, where, order by, return. It provides a structure very similar to SQL select, from where. Order by for iterates over a sequence, like assigns variables, where filters, order by sorts, and return constructs the result for each item in the iteration. It's a very powerful way to structure complex queries.
That sounds quite familiar, actually, coming from a database background.
It was designed to feel familiar to SQL users deliberately. XQuery also supports functions and modules, so you can build reusable libraries of query logic.
So when to choose XQuery versus XSLT? Quick rule of thumb.
Rule of thumb. If your primary goal is querying, filtering, aggregating data, especially from large XML datasets or databases, XQuery is usually the better fit. If your primary goal is transforming the structure of an XML document, maybe into a radically different XML structure or into HTML, XSLT often excels. They have overlapping capabilities, but different sweet spots.
Got it. Complementary tools. Now, both DOM and XDM load things into memory. What if the XML is just too big? Gigabytes, maybe. Or it's a continuous stream of data. Loading it all is impossible.
Right. For those scenarios, you need a different approach. Event-driven or sequential processing. Instead of building the whole tree in memory first.
You process it piece by piece as it comes in?
Exactly. The parser reads the XML sequentially, and as it encounters things, the start of an element, text content, the end of an element, it fires off events. Your application listens for these events and reacts immediately. The two main APIs for this are SX, simple API for XML, which is a widely implemented cross-platform standard. And in the .NET world, system.xml.xml reader.
SAX. I think I've heard of that one.
Yeah, it's been around a while. It actually grew out of early efforts to standardize how different XML parsers behaved, because initially they all worked slightly differently. SX provides a common event-based interface. In .NET, XML Reader is the forward-only, stream-based reader. It's very efficient. You can configure it using XML Reader settings, maybe tell it to ignore comments or white space to speed things up. And importantly for security, especially if the XML might reference external files, you can use something like XML Secure Resolver to limit where the parser is allowed to fetch external resources from, preventing potential attacks.
So much lower memory usage, processing on the fly. Ideal for huge files or streams.
Absolutely. The trade-off is that you don't have the whole document structure available at once, so certain kinds of processing that require looking backwards or forwards are harder.
Makes sense. Now, for developers specifically in the Microsoft .NET world, is there a more, let's say, integrated way to work with XML directly in C# or VB.NET code?
Yes, definitely. That would be LANQ to XML. LANQ stands for Language Integrated Query, and it's Microsoft's big push to make querying data, whether it's databases, objects, or XML, a natural part of the programming language itself. LANQ to XML provides a functional approach using simple .NET classes like XElement, XAttribute, XDocument. It makes creating, querying, and modifying XML feel much more native to the code.
So less awkward DOM manipulation.
Much less awkward. The code tends to be shorter and more legible, as our source puts it. You can construct XML trees programmatically, run LANQ queries over them using familiar syntax, and modify them in place. A particularly neat feature, especially in VB.NET, is XML literals. This lets you literally embed XML markup directly into your code.
You mean type angle brackets right there in the C# or VB?
In VB.NET, yes, directly. It looks like username, username, user. C# uses a slightly different syntax, but achieves a similar goal with functional construction. It really simplifies creating XML structures within your application logic. It feels very integrated.
That does sound convenient. Okay, let's connect this to the bigger picture now, databases. How do traditional relational databases, which love neat rows and columns, cope with this hierarchical, flexible, sometimes messy XML data? That seems like a fundamental mismatch, historically at least.
It absolutely was a major point of friction for a long time. You had the relational world optimized for tables and the XML world optimized for documents. A disparity, as the source calls it. But things evolved. Many major databases moved towards hybrid systems. They realized users needed to store both structured, tabular data and semi-structured XML data within the same database. Think of a complex purchase order, customer ID, order date that's relational, but the list of items with varying attributes and nested structures, that might be better stored as XML within the order record.
So getting the best of both worlds.
That's the goal. And some databases do it better than others. SQL Server, for instance, has really robust native XML features. It offers a native XML data type. This isn't just storing text. The database understands its XML and can index it intelligently. Then it provides methods you can use directly in your SQL queries to work with that XML data. Query executes an XQuery expression against the XML column.value, extracts a single scalar value like a string or number, exist checks if a certain node exists, useful and where clauses. Modify lets you insert, replace, or delete nodes within the XML using a subset of XQuery.
So you can update parts of the XML document right within SQL.
Exactly. And nodes is really useful. It shreds parts of the XML into a relational row set, so you can effectively join your XML data with regular tables. It bridges the gap. SQL Server also has 4 XML clauses, auto, path, explicit, which do the opposite. They take the results of a standard SQL query and format them as nested XML. Very handy for generating XML output.
What about other databases, like MySQL?
MySQL's native XML support has historically been more limited, as the source puts it. Often you'd store XML as TextST or BLOB types. It does have functions like extract value that allow some basic XPath querying over stored XML fragments, but it's not as deeply integrated as SQL